I'm so glad you found your way here tonight. Your brain is already doing something extraordinary right now. Something it only does when you allow yourself to rest. Tonight, you'll discover the quiet science of how your mind heals itself while you sleep. And by the end, you'll understand why every hour you give to rest is one of the most healing things you can offer yourself. Welcome to Sleepy Science Night. Wherever you are right now, perhaps in the dark with the quiet weight of the day still settling off your shoulders, perhaps already feeling your breath growing softer, allow yourself this slow arrival into stillness. We'll journey through 100 mind science facts about the healing that happens while you sleep. From the microscopic rivers that rinse your brain clean each night, to the way memory becomes permanent in the dark, to the silent repair that begins the moment your eyes close. This thoughtful journey through mind science builds a community of curious, restful minds. A gentle subscribe, a like, or sharing this with a friend who lies awake too long creates a pathway for more searching souls to discover this space, and brings us closer to keeping it here, one sleepy soul at a time. Let yourself settle completely here. Feel your jaw unclench, your shoulders drop, your hands open gently. You don't need to hold on to any of this knowledge tonight. Simply let these ideas drift through you like quiet water, washing gently past. Sense that soothing heaviness beginning to gather, like your consciousness is slowly dimming its lights, one room at a time, growing soft and still and safe. Close your eyes and breathe deeply. You're floating where memories rest safely in gentle darkness. Let your mind merge with infinite peace. And now we begin. Your brain never truly stops working. Even now, as you rest, it is one of the most metabolically active organs in your entire body. The brain makes up only about 2% of your body weight, yet it uses roughly 20% of all the oxygen and energy your body produces. During the day, it burns through resources at an extraordinary rate, processing information, managing emotion, regulating every system in your body. By the time night arrives, the brain has accumulated a measurable residue of its own labor, molecular byproducts, spent chemical signals, and proteins that need to be cleared away before morning. What happens next is one of the most beautiful stories in all of neuroscience. Sleep is not the absence of activity. It is the beginning of a different kind of work entirely. For most of human history, scientists assumed the sleeping brain was essentially idle. The body rested, and the brain rested too. That assumption turned out to be deeply wrong. Beginning in the 20th century and accelerating rapidly in recent decades, researchers discovered that sleep is filled with coordinated, purposeful biological activity, cascades of hormones released at precise moments, electrical waves moving through neural tissue with rhythmic intention, fluids flowing through channels that are largely sealed off during waking hours. Sleep is not passive. It is, in its own quiet way, one of the most organized performances the brain ever stages. Every night you sleep, you are giving your mind the conditions it needs to do things it cannot do any other time. The brain has its own waste-clearing system, discovered only within the last decade and a half. It is called the glymphatic system, a word that combines the word glial, referring to the support cells of the brain, with lymphatic, the drainage network used by the rest of the body. This system was first described in detail by neuroscientist Maiken Nedergaard and her colleagues at the University of Rochester, and its discovery quietly changed how scientists understand the purpose of sleep. The glymphatic system uses channels that run alongside blood vessels deep inside the brain, and through these channels, cerebrospinal fluid flows inward, mixing with the interstitial fluid between brain cells, and then flows back out again, carrying molecular waste with it. It is, in a very real sense, your brain's nightly rinse cycle. What makes the glymphatic system so meaningful is when it runs. Research has consistently found that glymphatic activity is substantially more active during sleep than during wakefulness. The system appears to be largely suppressed while we are awake and to open more fully once sleep begins. Scientists are still mapping exactly how much of this difference is driven by sleep state itself versus other contributing factors. But the directional relationship is well supported across multiple studies. Sleep enables clearance in ways that wakefulness does not. When sleep begins, particularly deep, slow-wave sleep, the channels open wider. Cerebrospinal fluid begins to move with greater force, and the cleaning begins in earnest. This is one reason scientists believe the brain needs sleep that cannot be replaced by simply lying still with eyes closed. The full activation of the glymphatic system appears to require the specific brain states that accompany genuine sleep, not rest alone. In October 2024, researchers at Oregon Health and Science University accomplished something that had never been done before in humans. Using a special imaging agent injected during neurosurgery in 5 patients, they captured direct visual evidence of the glymphatic system in the living human brain. For over a decade, the glymphatic network had been confirmed in animal models, but not yet definitively observed in people. That changed with this study. The perivascular spaces, the fluid-filled channels surrounding arteries deep in the brain, were now visible, traceable, and real in human tissue. As one of the lead researchers noted, people had believed these spaces were important. Now it was proved. What does the glymphatic system actually clear? Among the most important waste products it removes are amyloid, beta, and tau, 2 proteins that are produced as natural byproducts of normal brain activity every single day. In a healthy brain that sleeps well, the glymphatic system removes enough of them each night to support the brain's ongoing health. The system works with quiet efficiency, clearing these molecular residues in the dark hours while you rest. It is one of the most practical forms of self-care the brain has ever arranged for itself, and it requires nothing from you except the willingness to sleep. In January 2026, a study published in Nature Communications provided some of the first direct evidence in humans that the glymphatic system clears these proteins from the brain into the bloodstream during sleep. In a randomized crossover trial involving 39 participants, researchers measured morning plasma levels of amyloid beta and tau after normal sleep and after a night of sleep deprivation. After normal sleep, levels of these proteins were measurably higher in the blood, suggesting they had been cleared from the brain and moved into circulation. After sleep deprivation, that clearance was reduced. This is the mechanism working. This is the rinse cycle running, and it runs for you, quietly, every single night you allow yourself to sleep. The mechanical driver of glymphatic flow was identified in detail in January 2025 in a study published in the journal Cell. Researchers discovered that the pumping force behind cerebrospinal fluid movement during sleep is not the heartbeat alone, as previously assumed. It is driven by slow, rhythmic oscillations in a brain chemical called norepinephrine, synchronized with changes in blood vessel volume and cerebrospinal fluid flow during non-REM sleep. These oscillations create a gentle pumping action, vasomotion, that pushes fluid through the glymphatic channels with far greater efficiency than the simple pulse of the heart could manage alone. The brain engineers its own pump, and that pump runs on the rhythms of deep sleep. The same 2025 Cell study carried an important note about certain sleep medications. Zolpidem, one of the most commonly prescribed sleep aids, was found to suppress the norepinephrine oscillations that drive glymphatic flow. In animal models, this suppression led to measurably reduced cerebrospinal fluid movement during sleep. The study's authors observed that natural sleep and pharmacologically assisted sleep are not equivalent in their effects on brain clearance. This does not mean sleep medication is never useful. For many people, it plays a meaningful role, but it underscores why the quality and architecture of sleep matter, not just its duration. The brain's nightly cleaning depends on specific rhythms that unfold in their own time. Sleep position may influence how efficiently the glymphatic system works. Research using imaging in animal models has found that the lateral position, sleeping on your side, appears to support more efficient cerebrospinal fluid flow through the glymphatic channels compared to lying on your back or stomach. Scientists believe this is because the position affects how gravity interacts with the perivascular spaces. Whether this translates directly to meaningful differences in humans is still an active area of investigation, but it is one of the more intriguing suggestions to emerge from glymphatic research. The way you arrange your body while you sleep may quietly shape the cleaning that happens while you rest. Even the posture of rest has a kind of biology to it. Beyond the glymphatic system, sleep supports the brain through a network of immune cells called microglia. These cells are the brain's dedicated immune defenders. They monitor the environment around neurons, respond to damage, and clear away cellular debris. During wakefulness, microglia are partly occupied with monitoring and responding to the activity of a busy brain. During sleep, particularly during the deeper stages, their cleaning function becomes more prominent. They extend their processes into the spaces around neurons, engulfing damaged material, pruning weak or unnecessary synaptic connections, and maintaining the molecular landscape of the brain in ways that are not fully possible during the active demands of the day. The brain is also engaged in hormonal repair during sleep. Growth hormone, a molecule essential not just for childhood development but for adult tissue maintenance, metabolism, and cellular repair, is released in its largest daily pulse during the first cycle of deep sleep each night. A landmark study published in the journal Cell in September 2025, led by researchers at the University of California, Berkeley, mapped the neural circuits responsible for this release in precise detail for the first time. The researchers identified the specific brain pathways that trigger growth hormone pulses during both REM and non-REM sleep. and discovered a remarkable feedback loop. Sleep drives growth hormone release, and growth hormone then feeds signals back to the brain that help regulate the return to wakefulness. Sleep and repair are not separate processes. They are woven together in a single, continuously adjusting system. There is something quietly meaningful about this hormonal feedback loop, and this is offered as personal reflection, not a scientific claim. The body repairs itself most deeply precisely during the hours it is most still. The growth hormone that rebuilds muscle tissue, supports bone density, and maintains cellular integrity surges while the mind is absent from the conversation. You do not have to try to heal while you sleep. You only have to sleep. The healing has already arranged itself to meet you there. During sleep, the brain undergoes a process of emotional processing that is distinct from waking thought. Research has consistently shown that the sleeping brain, particularly during REM sleep, revisits emotional memories, but processes them in a neurochemical environment that is markedly different from wakefulness. During REM sleep, levels of norepinephrine, the stress-associated brain chemical, drop to their lowest point in the entire 24-hour cycle. Scientists have proposed that this creates a kind of safe container in which difficult memories can be replayed and integrated without the full physiological arousal they would trigger during wakefulness. The memory remains. The pain attached to it softens. This is one reason a difficult day often feels more manageable after sleep, and why sleep deprivation tends to amplify emotional reactivity. The way memory is stored permanently is one of the most active areas of sleep research. During the day, the hippocampus, a seahorse-shaped structure deep in the brain, acts as a temporary holding area for new experiences. It captures what you learn, what you feel, what you encounter, holding these records in a relatively unstable form. During sleep, particularly during the slow oscillations of non-REM sleep, the hippocampus communicates with the cortex, the outer layer of the brain, replaying recent experiences in compressed, rapid form. Over the course of these nightly conversations, memories are gradually transferred and stabilized in longer-term cortical storage. By morning, what you learned the day before has been quietly reorganized into a more permanent architecture. The mechanism of memory consolidation during sleep involves three interlocking brain rhythms that researchers have spent years learning to describe. The first is the slow oscillation, a broad, sweeping wave of neural activity that pulses across the cortex roughly once every 1 to 2 seconds during deep sleep. The second is the sleep spindle, a burst of faster electrical activity generated by the thalamus, the brain's relay station, lasting about half a second to 1.5 seconds. The third is the sharp wave ripple, a rapid, high-frequency oscillation generated in the hippocampus. When these three rhythms align in precise sequence, they create the conditions for memory transfer. The hippocampus replays a compressed version of a recent experience during the ripple. The spindle catches it and holds it briefly, and the slow oscillation provides the wider cortical context in which it is written. The brain is composing during sleep. A study published in the journal Neuron in April 2025 added a new molecular layer to this picture. Researchers discovered that during slow-wave sleep, cyclic adenosine monophosphate, a signaling molecule inside neurons. Exhibits its own infraslow oscillations, synchronized across the hippocampus and surrounding regions. These molecular oscillations, driven by norepinephrine beta-1 receptor activity, appear to create a kind of chemical window during which certain synapses become particularly susceptible to strengthening. Memory consolidation during sleep may not be a single process, but a nested series of chemical and electrical events unfolding at different timescales, each creating conditions for the next. The brain's nighttime library work is more layered than any single description captures. Synaptic homeostasis is a foundational concept for understanding what sleep does to the brain. The synaptic homeostasis hypothesis, developed by neuroscientists Giulio Tononi and Chiara Cirelli, proposes that during waking life, synapses, the connections between neurons, grow progressively stronger through learning and experience. By the end of a long day, the brain's synaptic landscape has been pushed toward a kind of saturation. During sleep, particularly during slow-wave sleep, the hypothesis suggests that synapses are selectively and globally scaled back, weakened in a controlled way, to restore the brain's capacity to learn again the following day. Sleep is, in this view, a form of calibration. It clears space for tomorrow by quietly releasing some of today. The selective nature of synaptic downscaling during sleep is what makes it so elegant. While overall synaptic strength is reduced during sleep, the connections that encoded meaningful, salient experiences during the day are relatively protected from this downscaling. They are the ones most likely to be replayed during hippocampal ripples. They are the ones whose molecular markers make them recognizable to the consolidation process. Important memories are kept. Less important connections are eased back. The sleeping brain is not erasing. It is curating. Every morning, you wake up. Your brain has already made quiet editorial decisions about what was worth holding on to. The sleeping brain also conducts what scientists call memory replay. During slow-wave sleep, the hippocampus reactivates the same patterns of neural firing that occurred during learning, but compressed, faster, stripped of unnecessary detail. If you spent an afternoon learning a new route through a city, the spatial map encoded in your hippocampal neurons will fire again during sleep, tracing the route in accelerated form, moving the experience toward cortical storage. Studies have measured this replay directly using electrode recordings, demonstrating that specific sequences of neuronal firing during waking experience reappear during subsequent sleep, often in the same order and with similar timing relationships. The brain rehearses in sleep what it experienced in waking. It just does so in a language of electricity too quiet to hear. REM, sleep. Rapid eye movement, sleep, appears to play a particularly important role in emotional memory and creative integration. During REM sleep, the brain is highly active. The eyes move rapidly beneath closed lids, and vivid dreaming most often occurs. The prefrontal cortex, the area of the brain most associated with rational, deliberate thinking, is relatively quiet during REM, while emotion processing areas such as the amygdala and limbic regions are more active. This combination seems to allow the brain to make associative connections between distantly related memories, linking new experiences to older ones in ways that do not follow the strict logical pathways of waking thought. Some researchers have suggested that this associative process during REM sleep underlies creativity, the feeling of waking with a solution that was not available the night before. The brain does not move through sleep in a single continuous state. Sleep is organized into cycles, each lasting roughly 90 minutes, that repeat 4 to 6 times across a full night. Each cycle includes stages of non-REM sleep: light sleep, deeper sleep, and the deepest slow-wave sleep, followed by a period of REM sleep. The proportion of each stage shifts across the night. In the early hours of sleep, slow-wave sleep dominates, and this is when glymphatic clearance and growth hormone release are most active. In the later hours, REM sleep becomes longer and more prominent, and emotional processing and creative consolidation intensify. A full night of sleep is not simply more of the same thing. It is a carefully sequenced program, each stage delivering something the others cannot. BDNF, brain-derived neurotrophic factor, is a protein that plays a crucial role in the health and survival of neurons. It promotes the growth of new neural connections, supports the maintenance of existing ones, and is essential for long-term memory formation. Sleep appears to support BDNF production and signaling. Research has found that sleep deprivation reduces BDNF levels in several brain regions, including the hippocampus. Good sleep, by contrast, supports the molecular environment in which the brain remains plastic, capable of learning, adapting, and recovering from its daily demands. Every night you sleep, you are providing the chemical conditions for your brain to remain resilient. The immune system and the brain are in quiet, constant communication during sleep. During slow-wave sleep, the body produces and releases cytokines, small signaling proteins that coordinate immune responses. Some cytokines appear to promote deeper sleep, creating a loop in which immune activity and sleep quality reinforce each other. When you are unwell, you sleep more, not merely because you feel exhausted, but because the immune system is actively using sleep to support its response. Research has shown that people who sleep fewer than 6 hours per night before receiving a vaccine may produce significantly fewer antibodies than those who sleep 7 or more hours. Sleep is not separate from immunity. It is where much of immunity happens. Cortisol, the body's primary stress hormone, follows a precisely timed cycle across the 24 hours of the day. During the evening and into the night, cortisol levels fall to their lowest point, creating the low arousal, low-stress neurochemical environment that deep sleep requires. In the early morning hours, cortisol begins to rise again, gently preparing the brain and body for waking. This rhythm is not just a reaction to sleep, it is an active driver of it. When cortisol remains elevated at night, through chronic stress, anxiety, or irregular schedules, it competes with the conditions sleep needs to begin. When cortisol drops on schedule, it creates space for the other hormones and rhythms of healing to step forward. The body has organized sleep around its own chemistry, and that chemistry is waiting, every night, to do its work. Melatonin is the hormone most directly associated with the body's transition to sleep. It is produced by a small gland called the pineal body, located deep in the center of the brain, and its release is triggered by darkness. As light fades in the evening, the pineal body begins secreting melatonin into the bloodstream, signaling to the brain and body that night has arrived. Melatonin does not cause sleep directly. It is not a sedative. It is a timing signal, a biological announcement that the conditions for sleep have arrived. Bright light in the evening, including the blue spectrum light emitted by screens, suppresses melatonin release, delaying the brain's transition towards sleep. The body's sleep signal is written in darkness. Let's pause here and notice your body. As you breathe out slowly, appreciate each tiny cell inside. Trillions of organisms working in silence. Heart beating, lungs breathing, brain thinking, all without your command. Notice the gentle sensations on your skin, in your muscles, along your spine. Your brain right now is not resting. It is working differently, clearing, remembering, repairing, all on your behalf and without any effort from you. You only need to be still. That is enough. That is, in fact, everything. Now we continue. The timing of sleep matters as much as its duration. The body's circadian rhythm, the internal 24-hour clock, is coordinated by a cluster of roughly 20,000 neurons in the hypothalamus called the suprachiasmatic nucleus. This tiny structure receives light signals from the eyes and uses them to synchronize the body's hormonal rhythms, temperature cycles, and metabolic processes with the light-dark cycle of the natural world. When sleep aligns with the circadian rhythm, when you sleep during the night hours, your biology expects the healing processes of sleep unfold in their proper sequence. When sleep is shifted by shift work, jetlag, or irregular schedules, the sequence is disrupted. Biology has a preferred timing for rest, and it has arranged the body's repair systems around that preference. Core body temperature drops by roughly 1 to 2 degrees Fahrenheit in the hours before and during sleep. This temperature drop is not incidental. It is part of the machinery of sleep onset. The brain uses a falling core temperature as one of its primary signals to initiate the physiological transition to sleep. Heat loss occurs primarily through the hands and feet, which is why people sometimes find that warming their feet helps them fall asleep. Dilating the blood vessels of the extremities speeds heat loss from the body's core, accelerating the temperature drop that triggers sleep. The body is always managing the conditions for its own healing, and temperature is one of the tools it uses most reliably. Adenosine is the chemical that creates the sensation of sleepiness across the day. It is a byproduct of neural activity. Every time a neuron fires, adenosine accumulates in the surrounding tissue. Over the course of a waking day, adenosine builds up progressively, creating what researchers call sleep pressure, the mounting biological drive to rest. Caffeine works by blocking the brain's adenosine receptors, preventing the molecule from signaling fatigue. But the adenosine itself continues to accumulate behind the blockade, which is why the fatigue returns, often suddenly, when caffeine wears off. During sleep, adenosine is gradually cleared, and sleep pressure dissipates. Morning wakefulness is, in part, a brain that has been rinsed of the chemical residue of yesterday. The hippocampus, the brain's primary memory formation structure, has a storage capacity that is not unlimited. As the day progresses and new experiences accumulate, the hippocampus fills with temporary records that need to be transferred elsewhere to make room for more. Sleep appears to serve partly as this transfer process. During the slow oscillations of non-REM sleep, recent hippocampal memories are replayed and gradually moved to distributed storage across the cortex. After a full night of sleep, the hippocampus is, in effect, partially emptied and ready to receive new information again. Studies have shown that people who take naps, even brief ones of 60 to 90 minutes, demonstrate improved hippocampal learning capacity in the afternoon compared to those who remain awake through the day. Sleep refreshes the brain's capacity to learn, not just its sense of energy. During REM sleep, the brain shows a pattern of activity in certain regions that is, in some ways, more intense than during waking. Areas associated with visual processing, emotional memory, and autobiographical narrative fire with unusual vigor during dreaming. The prefrontal cortex, normally the seat of critical evaluation and logical oversight, becomes much quieter, which may explain why dreams feel so real and yet so unconstrained by ordinary rules. What the brain is doing during this heightened, loosely supervised activity is not fully understood, but one well-supported idea is that it is testing connections, pulling together distantly related memories, checking them against each other, finding patterns that waking logic would not have noticed. The dreaming brain is not confused. It is exploring. The word consolidation, in the context of memory and sleep, refers to the process by which a freshly formed, fragile memory becomes stable. A newly encoded memory is initially stored in a form that is vulnerable, easily disrupted by interference, by stress, by time. Consolidation is the process by which it becomes resilient. Embedded in the longer-term architecture of the brain, sleep accelerates and deepens this process substantially. Research across many studies has shown that sleeping after learning, even a nap of an hour or two, significantly improves memory retention compared to remaining awake for the same period. The sleeping brain is not pausing the work of the day. It is completing it. The relationship between sleep and emotional regulation is one of the more immediately recognizable aspects of sleep science. Most people have experienced it directly. A night of poor sleep makes emotional reactions faster, stronger, and harder to modulate. Brain imaging studies have shown that sleep deprivation significantly increases the reactivity of the amygdala, the brain's primary threat detection and emotional response center, to negative stimuli, while simultaneously reducing the strength of the connection between the amygdala and the prefrontal cortex that normally helps regulate those reactions. These effects have been most clearly documented after full nights without sleep, though partial restriction across multiple nights shows similar, if sometimes subtler, patterns. After good sleep, this balance is gently restored. Sleep is the quiet return of emotional steadiness. The brain's glial cells, the support cells that surround and maintain neurons, play a role in sleep-dependent healing that is only beginning to be understood. One type, the astrocytes, are directly involved in glymphatic function. They bear water channels called aquaporin 4 on their surfaces that help regulate the flow of cerebrospinal fluid through the brain's tissue. Another type, the oligodendrocytes, produce the myelin sheath that insulates neurons and allows electrical signals to travel quickly and efficiently. Research has found that myelin production increases during sleep. The brain does some of its most important wiring work while you rest. The infrastructure of thought is built, maintained, and tended to in the hours you do not remember. Slow wave sleep, the deepest stage of non-REM sleep, characterized by large, sweeping electrical oscillations across the cortex, is the stage most closely associated with physical restoration. During slow-wave sleep, in addition to glymphatic activity and growth hormone release, the immune system is most active in its repair functions. Tissue is rebuilt, and the energy molecules that fuel neural activity are replenished. The proportion of slow-wave sleep that people experience tends to decline with age, which partly explains why older adults often feel less restored by sleep, even when sleep duration remains roughly the same. The deepest sleep, where much of the most fundamental repair happens, becomes harder to access as the decades pass, which is one reason that tending to sleep quality across a lifetime may be one of the gentler, more lasting forms of care a person can offer their own mind. Sleep spindles, the rapid bursts of electrical activity generated by the thalamus during non-REM sleep, are one of the most actively studied elements of the sleeping brain. Each spindle typically lasts between half a second and 1.5 seconds, brief enough to pass unnoticed, frequent enough to shape the night. In most healthy adults, spindles occur roughly 1 to 4 times per minute during non-REM sleep, with density varying across individuals and sleep stages. The density of spindles appears to rise after days of intensive learning, as if the brain scales its overnight work to match the demands placed on it. Spindles are associated with the consolidation of declarative memory, the kind of memory that holds facts and events. The brain seems to produce more of them after a day of heavy learning, quietly adjusting its overnight processing to honor what the day required. The relationship between sleep and creativity has been studied carefully and consistently. REM sleep, in particular, appears to support what researchers call remote associative thinking, the ability to connect concepts or ideas that are not obviously related. In one well-known experimental design, participants were given a mathematical problem that could be solved either by a laborious series of steps or by recognizing a hidden rule that made the solution much faster. Participants who slept between learning and testing were roughly 3 times more likely to discover the hidden rule than those who remained awake. The sleeping brain had found the shortcut. It had made a connection that waking, focused thinking had not. Sleep opens doors that effort keeps closed. The circadian rhythm influences not just when sleep happens, but how different biological repair processes are timed across the night. The liver, the heart, the gut, the immune system, all operate on circadian schedules, coordinated with the brain's central clock. During the night hours, liver cells clear metabolic byproducts on a circadian schedule. The gut microbiome shifts its composition and activity, blood pressure follows a nightly dip that is associated with cardiovascular health. The brain is not the only organ tending to itself during your sleep. The entire body is reorganizing around the biology of night, running processes that are specifically adapted to the quiet, low-demand hours of darkness. Sleep is a whole-body event in which the brain is both participant and conductor. Temperature management during sleep is more thoughtful than it might appear. As you move through different sleep stages, your body temperature continues to shift. During REM sleep, the body's temperature regulation, the normal process of adjusting body temperature in response to the environment, is largely suspended. You become, in effect, temporarily ectothermic, your body temperature drifting closer to the ambient temperature around you. This is why sleeping in a room that is too hot or too cold can disrupt REM sleep significantly. The brain, during its most complex and emotionally rich sleep stage, has traded the energy cost of temperature regulation in order to sustain the particular neural activity that REM requires. Even in rest, the brain makes gentle trade-offs. The connections between sleep and long-term brain health are among the most studied areas in contemporary neuroscience. Large epidemiological studies have found that persistent short sleep, habitually sleeping fewer than 6 hours per night, in people in their 50s and beyond, is associated with elevated risk of cognitive changes in later life. The proposed mechanism involves the glymphatic system and the gradual accumulation of molecular waste that ongoing clearance is designed to prevent. Sleep deprivation is not the only factor in this picture, and the relationship runs in both directions. Disrupted brain health can also affect sleep, but the connection is well established, and the implication is a gentle one. Sleep, practiced consistently across the years, is a form of quiet investment in the mind's future. The concept of sleep debt is real and measurable. Each hour of missed sleep accumulates in the brain as a physiological deficit that affects cognitive performance, emotional regulation, and the body's capacity for repair. Studies have shown that people who sleep 6 hours a night for 2 weeks demonstrate cognitive deficits comparable to those seen after 2 full nights without sleep. Yet they report feeling only mildly sleepy, because chronic sleep restriction also impairs the subjective sense of fatigue. Tonight, simply being here is already adding to the account. The body notices every hour you give it. You're still here, still listening, still somewhere between waking and drifting. That's exactly where you should be. Take a slow breath. Notice how your thoughts have grown a little softer, a little less insistent. We're moving through the science of your own mind together. You and I and everyone else who found their way here tonight. There is no rush, just the gentle pull of one quiet fact after another. Let's continue. The brain's default mode network, a set of regions including the medial prefrontal cortex, posterior cingulate cortex, and parts of the hippocampus, is active during quiet, inwardly focused states, including daydreaming, self-reflection, and the twilight of falling asleep. This network has been linked to the processing of social information, the construction of autobiographical narrative, and the projection of future scenarios. During sleep, particularly in the early stages and during REM, default mode network regions show complex patterns of activity that may be related to the integration of personal experience into long-term self-understanding. The mind, even in its most relaxed state, is actively building the story of who you are. Napping science has become increasingly thoughtful. Research has distinguished between different nap durations and their different effects on the brain. A brief nap of 10 to 20 minutes, sometimes called a power nap, primarily involves light, non-REM sleep and produces a short burst of improved alertness and reduced fatigue without the grogginess associated with waking from deeper sleep. A nap of 60 to 90 minutes allows entry into slow-wave sleep and produces more substantial memory consolidation benefits, particularly for declarative memory. A full 90-minute nap that includes a complete cycle ending in REM sleep supports emotional processing and creative insight as well. The brain uses whatever sleep it can access. Even brief, imperfect rest is recognized and honored. Acetylcholine is a neurotransmitter that plays a particularly important role in REM sleep. During waking, acetylcholine levels in the brain are elevated and support attention, arousal, and focused cognition. During non-REM sleep, acetylcholine drops significantly, and the brain's processing shifts toward the broad, slow oscillations of consolidation. During REM sleep, acetylcholine surges again, nearly to waking levels, which is one reason REM feels neurologically similar to wakefulness in some ways. Vivid, emotionally rich, associatively free. The brain uses the same chemical alphabet in waking and dreaming, but assembles the words differently. Consciousness and dream consciousness are not opposites. They are two arrangements of the same materials. The hippocampus, during sleep, does not replay memories randomly. Research has found that it preferentially replays experiences that were associated with reward, novelty, or emotional significance during the waking day. A new experience that moved you, a moment of genuine connection, a problem that required real effort to solve. These are more likely to appear in hippocampal replay during subsequent sleep than routine, unremarkable events. The brain, it seems, has already decided what was worth saving before the replay begins. The sleeping mind curates, but the waking mind had already cast the first vote about what deserved to be kept. The relationship between sleep and pain is well documented and often underappreciated. Adequate sleep raises pain thresholds, the amount of physical discomfort required to register as genuinely painful. The mechanism involves multiple systems, including the brain's endogenous opioid and endocannabinoid pathways, which are both influenced by sleep quality. During deep sleep, the brain's descending pain modulation pathways are in a state of relative calm, less inclined to amplify incoming pain signals, more inclined to simply let the body rest. Good sleep does not eliminate pain, but it tends to make it more bearable, more manageable, more distant from the center of attention. Rest changes the distance between you and what hurts. The body repairs cellular DNA during sleep. Throughout the waking day, cells sustain minor DNA damage through normal metabolic activity, environmental exposure, and the simple wear of being alive. during sleep, particularly during the deeper stages. Repair enzymes are active in seeking out and tending to these small breaks and errors in the genetic code. Sleep provides the low demand, low arousal conditions in which this molecular maintenance can proceed without competition from the body's more urgent waking priorities. Every night, in the quiet of rest, the body is tending to the most fundamental architecture of its own existence. Dreaming appears to serve multiple functions, and researchers continue to refine their understanding of exactly what those functions are. One well-supported idea is that dreaming provides a kind of simulation space, a place where the brain can process and rehearse emotional situations, particularly challenging ones, in a context that carries no real-world cost. Another idea is that dreaming reflects the associative integration process happening during REM sleep. The dream narrative is, in a sense, the felt experience of the brain connecting disparate memories and building new associations. Perhaps both are true. Perhaps dreaming is the story the narrative mind tells itself about the statistical work the brain is quietly completing in the background. We feel in stories what the brain does in numbers. The sleeping brain remains partially responsive to the external world, even in deep sleep. Studies have shown that meaningful sounds, such as a person's own name or the cry of a baby, are processed differently by the sleeping brain than neutral sounds of equivalent volume. The brain continues to monitor its environment, maintaining a light vigilance even during what appears from the outside to be complete unconsciousness. This monitoring is not random. It is tuned to signals that carry potential significance for safety. The sleeping brain is not absent. It is filtering. It is listening for what matters, while setting aside what doesn't, while conducting all of its healing work simultaneously. The immune cells, called T cells, which help protect the body against infection, are produced and released in greater numbers during sleep. Researchers found that natural killer cells, part of the immune system's first line of defense, are influenced by sleep quality in measurable ways. Rest is immune function. They are not separate processes operating in parallel. They are the same biology, organized around the same nightly opportunity. Every hour of sleep is a contribution to the body's capacity to protect and maintain itself, quietly and without any announcement. Halfway through our journey tonight, and here is what the science is revealing. Fact by fact, the mind does not heal itself despite sleep. It heals itself through sleep. Every stage, every rhythm, every chemical cascade we have encountered is a piece of the same patient architecture. A system evolved across millions of years to take advantage of the quiet hours of darkness for the work that cannot happen in the light. The brain's nightly self-repair is not a side effect of sleep. It is one of sleep's primary purposes. You are not just resting right now. You are, in a very real sense, being tended to. Let each breath guide you to realize that time is yours, a separate stream that only you are living. While the vast universe continues to spin, expand, change, this moment, this breath you are taking right now, is unique. Right now, your brain is doing something it cannot do at any other hour of your day, and you are giving it exactly what it needs by simply being here, by simply being still. Cherish this present moment, knowing that right now, your time is doing something quiet and extraordinary. And we continue drifting. The word restoration, when applied to sleep, turns out to be more literal than it sounds. Multiple systems in the brain and body are not merely resting during sleep. They are actively replenishing resources that were consumed during wakefulness. Glycogen, the brain's stored form of glucose, is replenished in astrocytes during sleep. Neurotransmitter precursors are synthesized and restocked. Cellular proteins that have experienced the metabolic stress of activity are degraded and replaced. The word restoration implies return to a previous state. And that is approximately what happens. Each morning, the brain wakes as close to its optimal condition as its overnight repair has been able to manage. How close that is depends, in large part, on how fully and how deeply you slept. The autonomic nervous system, which controls heart rate, digestion, respiratory rate, and a host of unconscious biological functions, shifts significantly during sleep. During non-REM sleep, the parasympathetic branch of the autonomic nervous system becomes dominant. This is the system associated with rest, digestion, and recovery, sometimes described as the rest and digest system in contrast to the fight or flight system. Heart rate slows, blood pressure drops, digestive activity increases, and the inflammatory tone of the body is gently reduced. Across a full night of sleep, the parasympathetic system has the longer turn. The body uses the night to tend to itself in the way it cannot during the demands of the day. Sleep has a measurable relationship with cardiovascular health. Blood pressure typically follows a pattern of nocturnal dipping, falling by 10 to 20% during sleep, that is associated with lower long-term risk of heart disease and stroke. People whose blood pressure does not dip during sleep face elevated cardiovascular risk over time. The mechanisms are multiple. The reduced heart rate and blood pressure during sleep provide direct rest for the heart muscle, while the reduction in stress hormone levels and inflammatory signaling during sleep reduces arterial wall stress across the years. Sleep is, among other things, when the heart rests most deeply, and the heart, like the brain, benefits from that rest across a lifetime. The brain's prefrontal cortex, the area most associated with planning, judgment, impulse control, and complex decision-making, is among the most sensitive brain regions to sleep restriction. Even modest sleep reduction produces measurable changes in prefrontal cortex activity and blood flow, affecting the nuanced, higher-order functions this region supports. Studies have found that sleep-restricted individuals make less carefully evaluated decisions, have reduced access to creative problem-solving, and show diminished flexibility in their thinking. The most thoughtful functions of the human brain, the ones that make us most fully ourselves, are among those that depend most directly on adequate sleep. It is not the routine operations that soften first. It is the distinctly human ones. The sleeping brain produces electrical patterns that can be measured and decoded from outside the skull using electroencephalography. The characteristic waves of each sleep stage, the slow, rolling delta waves of deep sleep, the faster theta waves of lighter sleep, the rapid, mixed activity of REM, have been mapped in detail since the mid-20th century. Researchers can now identify individual sleep stages from these recordings with high accuracy, and increasingly, they can use the patterns to infer what kinds of processing the brain is engaged in. Some research groups have shown that it is possible to identify, from sleep EEG recordings, which of several images a person was shown before sleep, based on the pattern of their subsequent slow oscillations. The brain is writing its memories in a script that, with patience and technology, can be partially read. The experience of hypnagogia, the transitional state between wakefulness and sleep, is one of the most scientifically interesting and experientially gentle aspects of the sleep onset process. During hypnagogia, people commonly experience vivid imagery, the faint sensation of hearing their own name, sudden muscle relaxation called hypnic jerks, and a quality of thought that is more associative and loosely bounded than waking cognition. The brain during this transitional state is moving between attentional modes, releasing its grip on focused, linear processing, and beginning to drift toward the pattern of activity characteristic of sleep. Hypnagogia has been noted, historically, as a doorway to unusual insights for artists and scientists who learn to rest their attention at the edge of sleep. You may be approaching that doorway right now. Neurons in the sleeping brain show a phenomenon called down states, brief periods during slow-wave sleep when groups of neurons essentially pause their firing simultaneously. These pauses, lasting a fraction of a second, are coordinated across large areas of the cortex in a rhythmic pattern. The down states alternate with up states, periods of synchronized neural firing that closely resemble the patterns seen during wakefulness. This alternation between up and down states produces the characteristic slow wave of deep sleep. Scientists believe the down states provide a period of genuine rest for individual neurons, a brief silence during which the metabolic processes of recovery can proceed at the cellular level. Even within sleep, even within the deep work of healing, there are moments of absolute stillness, rest within rest, quiet within quiet. The gut and the brain are in constant communication through the vagus nerve, a long, winding nerve that carries signals in both directions between the digestive system and the brain. During sleep, this communication takes on a particular character. The gut produces serotonin, a neurotransmitter closely associated with mood and well-being, largely during the night. The composition of the gut microbiome, the trillions of bacteria that live in the digestive tract, shifts across the circadian cycle in ways that appear to influence the production of neurotransmitter precursors that feed into brain chemistry. Sleep, good digestion, and emotional balance are more interwoven than they appear from the outside. The healing of sleep is a whole-body process that includes, in ways science is still mapping, the living ecosystem inside you. The brain's ability to form long-term memories depends on protein synthesis, the building of new proteins within neurons. This synthesis is necessary for the physical structural changes that constitute a stable long-term memory, and it appears to require periods of quiet, low arousal activity in the brain to proceed efficiently. Sleep, with its reduced norepinephrine levels and its coordinated slow oscillations, provides these conditions. Some research has suggested that the periods of neural silence during slow-wave sleep-down states are particularly important for the protein synthesis underlying memory consolidation. The molecular machinery of memory, the actual building of new biological structures within neurons, runs most smoothly in the quiet. It needs a still room. The blood-brain barrier, the highly selective membrane that controls what enters and exits the brain from the bloodstream, appears to undergo its own maintenance during sleep. Some research has suggested that sleep deprivation can affect the integrity of the blood-brain barrier over time. Conversely, good sleep appears to support the maintenance of barrier integrity. The brain is not just healing its neurons and clearing its waste during sleep. It is also tending to the structures that protect it from the wider world. The boundaries of the brain, like everything else inside it, are maintained by rest. The thalamus, during sleep, plays an important role in protecting the sleeping brain from interruption. In a mechanism sometimes called thalamic gating, the thalamus, which during wakefulness relays sensory information from the body and environment up to the cortex, begins, during sleep, to suppress the transmission of incoming sensory signals. This suppression is not absolute. Meaningful sounds still pass through. Sudden, unexpected stimuli can break through. But routine sensory information, background noise, minor physical sensations, is filtered at the thalamic gate, preventing it from reaching the cortex and interrupting the consolidation work underway. The sleeping brain has appointed its own guardian. It has arranged to be undisturbed unless something truly requires attention. The locus coeruleus, a small cluster of neurons in the brainstem responsible for producing most of the brain's norepinephrine, plays a unique role in both wakefulness and sleep. During waking, it drives attention and arousal. During sleep, its activity drops gradually, reaching its absolute lowest during REM, which is why norepinephrine falls so steeply during dreaming sleep. This drop is part of what creates the neurochemical environment in which emotional memories can be replayed and processed without triggering the full stress response they might generate during wakefulness. The locus coeruleus is, in a sensor, the switch between two modes of the brain's operation: the vigilant, responsive mode of day and the quiet, integrative mode of night. Research in 2025 added new precision to our understanding of memory time windows during sleep. The study published in Neuron identified that specific molecular oscillations in the hippocampus during slow-wave sleep create brief windows, measured in seconds, during which synaptic strengthening is most likely to occur. This suggests that memory consolidation during sleep is not continuous, but happens in discrete moments within a larger rhythm. The sleeping brain has not just one process running, but a sequence of nested cycles, each creating the conditions for the next. Memory is not simply written during sleep. It is written during particular instants within sleep, when the chemistry and electricity briefly align. The science of targeted memory reactivation has opened a new window onto what the sleeping brain can do. Researchers have discovered that playing sounds or scents associated with learning during subsequent sleep, while the person is in non-REM sleep, can strengthen specific memories without waking the sleeper. The associated sensory cue appears to trigger hippocampal replay of the linked memory, adding an extra rehearsal to the consolidation process. A 2025 study published in the journal NPJ, Science of Learning, showed that personalizing this stimulation to each individual's retrieval performance significantly enhanced consolidation of difficult memories, reducing memory decay and improving error correction. The sleeping brain, it turns out, can be gently guided, but it must be asleep to receive the guidance. The relationship between sleep and learning is reciprocal in both directions. Good sleep before learning prepares the hippocampus to encode new information efficiently, clearing the memory buffer so it can receive new material. Good sleep after learning consolidates what was encoded, moving it toward long-term stability. And the amount of learning during the day influences the intensity of sleep-dependent processing that follows, as if the brain measures its own demand and scales its nightly work accordingly. Sleep is not merely a recovery period bookended around learning. Sleep and learning are interleaved, each enabling and shaping the other. They are parts of a single, continuous process of understanding that stretches, unbroken, from your first waking moment to the deepest hours of the night. The brain during sleep shows remarkable sensitivity to its thermal environment. Even small changes in ambient temperature, a room that grows a few degrees warmer or cooler during the night, can shift the proportion of slow-wave sleep and REM sleep without the sleeper being consciously aware of the change. Research has found that ambient temperatures between approximately 60 and 67 degrees Fahrenheit tend to support a gentle sleep architecture for most adults, allowing the core body temperature drop that deep sleep requires without the involuntary arousal that comes from cold. The room itself is part of the healing. The environment of sleep shapes the biology of sleep in ways that are quiet, consistent, and largely unconscious. During sleep, the brain's pain-modulating systems undergo recalibration. The descending pain modulation pathways, neural circuits that travel from the brain down to the spinal cord and regulate pain signals traveling upward, are influenced by sleep stage and sleep quality. During deep sleep, these pathways are in a state that reduces pain amplification, meaning the brain is less inclined to magnify incoming pain signals. The brain does not just rest its way away from pain. It actively adjusts the circuits that decide how present pain feels. After a good night of sleep, what hurt the evening before sometimes feels lighter. This is not imagination. It is the recalibrated nervous system. The process of falling asleep requires a loosening of the executive control systems that maintain focused, sequential waking thought. The prefrontal cortex begins to quiet. The thalamus begins its gating function. The attentional networks that hold the mind directed toward a single task begin to soften and dissociate. This loosening is not a failure. It is a necessary opening. The mind, in releasing its grip on directed thought, allows the brain to shift into the broader, more associative mode that sleep requires. For people who lie awake, the invitation is not to try harder. It is to allow the effort to dissolve. Sleep comes not when you pursue it. It comes when you are willing to let it find you. The science of REM sleep continues to expand in unexpected directions. Recent research has found that during REM sleep, the brain's visual cortex is reactivated in patterns that mirror the patterns produced by real visual experience during waking. The brain is, in a very meaningful sense, seeing during dreams. using the same neural machinery it uses to see the world. The experience of visual imagery and dreams is not metaphorical activity in a non-visual region. It is actual activation of the visual processing system, driven by internal signals rather than external light. The dreaming brain is not imagining sight. It is producing it. The question of what animals dream is one of the more philosophically gentle edges of sleep science. Birds, reptiles, and fish have been found to show something like REM, equivalent sleep states, suggesting that the evolutionary origins of this sleep phase are ancient. Rats have been shown to replay the spatial sequences they navigated during the day, running mazes in their sleep, in effect, using the same hippocampal neurons that fired during the original experience. The presence of something like dreaming in so many species suggests that whatever sleep does for the brain, it is valuable enough to have been conserved across hundreds of millions of years of evolution. The need to dream, or something like it, is one of the oldest needs a nervous system carries. The glymphatic system's activity during sleep depends significantly on the depth and continuity of sleep. Fragmented sleep. Sleep interrupted by frequent partial awakenings, even if the total duration seems adequate, is associated with reduced glymphatic flow. This is because the slow, synchronized oscillations that drive cerebrospinal fluid movement through the perivascular channels require sustained periods of non-REM sleep to fully develop and maintain their pumping rhythm. The cleaning requires patience. The brain's rinse cycle needs time to run. Tonight, by simply staying here, by allowing yourself this long and uninterrupted rest, you are giving that system exactly what it needs. There is a growing body of research suggesting that sleep plays a role in the immune system's memory as well as the brain's. Vaccination studies have found that people who sleep well after receiving a vaccine show stronger and longer-lasting antibody responses than those who are sleep-restricted in the days following vaccination. This appears to be because the immune system, like the brain, undergoes a form of consolidation. The information acquired through exposure to the vaccine is better integrated into lasting immune memory during adequate sleep. The immune system is learning, in a sensor, and sleep is when its learning is stabilized. The body uses the same overnight quiet for two different kinds of memory, and both are honored equally. Hormesis in sleep. The concept that the mild demands of the waking day actually prepare the body to use sleep more productively is an area of growing interest. Moderate physical exercise, for example, has been shown in multiple studies to improve sleep depth and glymphatic efficiency. Moderate intellectual challenge during the day appears to increase sleep spindle density at night. The brain seems to scale its overnight repair to the demands of the day, and a day that was genuinely engaging, not overwhelming, but substantively present, may produce a night that is more restorative than a day of complete passivity. The body prepares its own healing by engaging honestly with the world. The sleep of newborns and infants, who may spend 16 to 18 hours of every day asleep, is dominated by REM equivalent sleep to a remarkable degree. In the first months of life, roughly 50% of sleep time is spent in an active, high REM state, compared to roughly 20 to 25% in healthy adults. Scientists believe this reflects the extraordinary demand for neural construction during early development. The brain is building its architecture at enormous speed, and the active sleep state supports the synaptic growth, pruning, a neural pathway formation that this construction requires. Sleep, at the beginning of life, is when the brain assembles itself. It is not a pause from development. It is development's primary medium. The answer to the question this video began with, "Why does your mind heal itself while you sleep?" is now clear in its broad outline, though the details are still being added. The mind heals during sleep because sleep creates conditions that cannot exist during waking. The brain lowers its arousal chemistry, creating the quiet that allows fluid to flow, memories to be moved, synapses to be scaled, hormones to be released, and the molecular residue of the day to be cleared away. These processes are not incidental to sleep. They are its point. Every night, you lie down and let yourself drift toward unconsciousness. You are not escaping the demands of your life. You are meeting the deepest demand of all, the one your brain has been placing on you since the day you were born. You might be feeling very tired now. That's perfectly right. Breathe slowly. Feel the cycles moving through you, the breath in and out, the slow settling of your body, the rhythms the brain has been following without any help from you. Your neurons right now are oscillating in their slow, healing patterns. Your cerebrospinal fluid is moving through its quiet channels. Your hippocampus is doing its careful work. You don't need to hold on to any of this. Let everything unfold in its perfect order, like the tides that do not try to reach the shore, like water that simply flows where the landscape allows. We're almost there now. The brain during sleep is extraordinarily self-sufficient. It does not need your attention to heal. It does not need your help. All it needs is the absence of interference, the absence of light, noise, anxiety, and the effort of staying awake. Given that absence, it knows exactly what to do. It has known for the entire span of human existence. You have always been carrying this capacity for repair. Tonight, you are simply allowing it to run. Every hour of sleep you have ever had has contributed something. Even the nights that felt light, or broken, or restless. Each one delivered what it could. The brain has always been doing its best with what you gave it. And tonight, you are giving it something generous. You are giving it time. The slow oscillations of deep sleep move like weather across the cortex. Broad, low-frequency waves traveling from front to back, from back to front, sweeping the brain in rhythms as old as sleep itself. These waves do not announce themselves. They simply arrive and recede, the most patient rhythm in the body. They have been moving through sleeping brains for longer than language has existed to describe them. Myelin, the white insulating sheath that wraps around nerve fibers and allows electrical signals to travel with speed and precision, is produced most actively during sleep. The faster and more accurately a thought can travel from one part of the brain to another, the more myelin the pathway between them carries. Sleep is, among other things, the time when the brain's wiring is gently maintained. The infrastructure of thought is tended to in the hours you do not remember. The sleeping hippocampus replays not just recent memories, but connects them to older ones, weaving what happened today into the fabric of everything that came before. your personal history grows each night, without your knowing, in the quiet of sleep. The self you wake as has always been built partly in the dark. Breathing slows during sleep. Somewhere between 12 and 14 breaths per minute during wakefulness becomes 8 to 12 during non-REM sleep. The body uses less oxygen. The brain asks for less. In the quieter economy of rest, everything finds its lower, more sustainable rate. Even the breath becomes a kind of permission. Your brain's temperature drops slightly during sleep, independent of the body's core temperature drop. Cooler neurons are more energy efficient. The brain, during sleep, runs its repair and consolidation work on a lower, more sustainable metabolic flame, one that is precisely suited to the long, unhurried work of the night. Even efficiency has a biology. Even repair has its preferred conditions. During sleep, the body produces and releases cytokines, signaling proteins that support immune function and inflammation regulation. Some of these molecules also appear to promote deeper sleep, reinforcing the nightly cycle between rest and repair. The immune system is not waiting until morning to begin its work. It is already underway, using the hours of darkness to tend to what the day accumulated. Rest is immune function, and they share the same quiet hours. During REM sleep, the muscles of the body, except those controlling the eyes and breathing, are actively held still by the brainstem. This state is called REM atonia. It is not a failure. It is a protection, preventing the body from acting out the movements of dreams. The brainstem knows to hold the body still while the mind moves freely. Even in the deepest exploration, the body is kept safe. Even the wildest dream unfolds in a kept stillness. Growth hormone, released in its greatest pulse during early slow-wave sleep, supports not just muscle and bone, but also the health of neurons. It promotes cellular repair, protein synthesis, and metabolic regulation throughout the body and brain. The brain that sleeps well repairs well. The brain that is repaired works well. The cycle is designed to close on itself in kindness. Nothing about it requires effort on your part. You are already inside it. The ancient Greek physician Hippocrates believed that the conditions of the body were reflected in the quality of sleep, and that tending to sleep was tending to health. Modern science does not support every detail of his interpretation, but the intuition it reflects, that sleep is a time of biological significance, not mere absence, was more correct than the culture of his time could know. What felt like wisdom to him, science is now able to trace to specific molecules, circuit, and rhythms. In the language of neuroscience, the phrase offline consolidation refers to the stabilization of memory that occurs when the brain is not actively engaged with the environment. Sleep is the most complete form of offline processing available to the brain. It offers a period of quiet, deep enough, and long enough for the full architecture of memory to be reorganized. You learn in waking. You understand in sleep. Both halves matter. Neither is complete without the other. The aquaporin 4 channels on the surface of astrocytes, the water channels through which cerebrospinal fluid enters and exits the brain tissue, during glymphatic clearance appear to be sensitive to the body's circadian rhythm. Their expression changes across the 24-hour cycle, being most functionally organized during the sleep phase. The brain has timed its own cleaning system to the biology of night. It has arranged everything around the expectation that you will sleep. It was always waiting for you to arrive. Sharp wave ripples in the hippocampus. The rapid, high-frequency oscillations associated with memory replay last only about 100 milliseconds each. They are brief enough to be called moments. And yet each one contains a compressed representation of an experience, a spatial journey, a conversation, a face, an emotion, that the brain is quietly moving from temporary to permanent storage. Great work happens in small moments. The most lasting things are written in the briefest intervals. During sleep, the connections between neurons are not all treated equally. The synaptic homeostasis hypothesis proposes that overall synaptic strength is gently reduced during sleep. But the most meaningful connections, those formed by genuine learning and genuine experience, survive the scaling. What was truly important remains. The rest becomes background. Sleep curates the brain the way time curates a life, preserving what mattered, releasing what did not. The experience of waking with a feeling of clarity, when a problem that seemed closed the night before appears open in the morning, is not simply a metaphor for rest. It reflects real changes in how the brain has processed the information during sleep, making new connections, integrating emotional context, and finding pathways through problems that were obscured by the narrowed thinking of late-day fatigue. Sleeping on it works. The brain was working while you slept. It was working for you. Sleep supports the body's inflammatory balance. While inflammation is one of the body's primary healing tools, the body also needs periods of lower inflammatory tone to restore and maintain its systems. Sleep provides some of these conditions. Research has found that adequate sleep is associated with more balanced inflammatory markers in the bloodstream. Not the absence of inflammation, but its healthy regulation. The body uses the night not to suppress its defenses, but to calibrate them. Every night of adequate sleep is a small contribution to that calibration. The word rest, in its deepest biological meaning, does not mean absence. It means a different kind of presence. The presence of repair, of consolidation, of the quiet systems that cannot operate when the loud systems of waking are running. You are not away right now. You are somewhere else inside yourself, somewhere more fundamental, somewhere the day cannot reach. This is not withdrawal. This is return. The brain's reward circuits, including the dopaminergic pathways associated with motivation, pleasure, and the anticipation of good outcomes, are significantly influenced by sleep quality. Good sleep supports a balance between desire and judgment. The rested mind can want things without being controlled by wanting them. It can stay with difficulty without being overwhelmed by it. It can move through the day with the kind of equanimity that exhaustion tends to erode. Sleep restores not just the capacity to think, but the capacity to be at ease inside a day. Scientists who study sleep often describe it not as a passive state, but as the brain's most organized state. During wakefulness, neural activity is diverse, noisy, and reactive, responding moment by moment to an unpredictable environment. During sleep, that activity becomes coordinated, patterned, and purposeful in ways that waking activity rarely achieves. The slow oscillations of deep sleep sweep the cortex with extraordinary regularity. The spindles pulse at their measured intervals. The hippocampal ripples fire in timed coordination with the cortical waves. Sleep is not where organization breaks down. It is where the brain's deepest organization finally becomes visible. The relationship between sleep and learning is so consistent across studies that sleep researchers sometimes describe sleep as the second half of learning. The half that actually makes what you encountered during the day stay with you across time. If waking is where you gather, sleep is where you keep. The two halves complete each other. Neither alone is enough, and together they are more than the sum of what they accomplish separately. Every night that you sleep, you are participating in a process that is, in one sense, as old as complex life on Earth. The need for sleep appears in virtually every animal with a nervous system, from the simplest worms to the most cognitively complex mammals. Whatever sleep does for a brain, it has been worth the vulnerability of unconsciousness for hundreds of millions of years of evolution. Life has never found a way around sleep because nothing about life has made sleep unnecessary. It is not an inefficiency. It is the condition everything else depends on. The most recent years of sleep science have produced a picture that is more intricate, more purposeful, and more humble than anything researchers imagined when the field began. The glymphatic system. The precise choreography of norepinephrine oscillations driving cerebrospinal fluid flow. The discovery of specific molecular time windows for memory consolidation. The mapping of the neural circuits that gate growth hormone release. Each discovery has revealed not simplicity, but extraordinary complexity. A brain that has organized itself around the need for sleep with a thoroughness that keeps exceeding what scientists expect. The more closely the sleeping brain is studied, the more it turns out to be doing. What is being tended to during sleep is not only the brain in a medical sense. It is, in a broader and more personal sense, the conditions for being yourself, the capacity for clear thought, the ability to feel without being overwhelmed, the reach of curiosity, the patience to hear another person, the courage to try again tomorrow. These things are supported by sleep in ways that are real, biological, and increasingly well understood. Sleep is the maintenance of the self. Every night, in the dark, you become more fully what you are. And so this is the final fact, and it is the simplest one. Your brain has spent this entire night, every night of your life, quietly, methodically, patiently tending to itself. It began before you knew the word neuroscience. It will continue long after this video ends. There is nothing you need to do to earn this repair. You only need to allow it. And you are here, right now, in the dark, allowing it. That is enough. That was always enough. The healing was always already happening. And so our quiet journey through the science of the healing mind comes gently to a close. We traveled from the microscopic rivers of the glymphatic system, those extraordinary channels through which cerebrospinal fluid moves in slow, oscillating waves. carrying the molecular residue of thought out into the body, to the sharp wave ripples of the hippocampus, each one lasting only 100 milliseconds, each one quietly moving a piece of your life into the permanence of long-term memory. We discovered that the brain never truly stops working, only that it works differently in the dark, and that its work in the dark is, in many ways, its most important work of all. Along the way, we touch the biology of why rest supports the mind across a lifetime, why the quality of each night matters, and why the simple act of lying down and allowing yourself to rest is one of the most genuinely healing things a human being can do. Sleep science reminds us that much of the most meaningful work of the mind happens in silence, in the hours no one sees. In the architecture of the unconscious night, the brain does not need an audience to tend to itself. It does not need acknowledgement. It simply does its work, every night, without fail, as long as it is given the chance. By pausing to understand this, we glimpse something quietly extraordinary about what we are and what we carry forward, rested, into every morning. In these final minutes, take the deepest breath you can, as deep as possible. Think about unity, of every oscillation, every ripple, every slow wave moving through the brain in this moment. You are not separate from this. You are inside it. Right now, as you breathe, the cerebrospinal fluid is moving through the channels of your brain, carrying the day's residue gently outward. The hippocampus is quietly composing. The synapses are settling toward their morning balance. You are not watching this happen. You are this happening. Let your entire being dissolve into the gentle dark, into the soft, unhurried rhythm of your own healing mind. Prepare for deep sleep. No boundaries left, only peace. If this gentle journey through the science of your sleeping mind brought you any stillness tonight, a softer breath, a quieter thought, a little more permission to rest, perhaps share it softly with someone else who lies awake too long. A quiet like, a subscribe, a word to a friend. It might be the thing that helps one more searching mind find its way to rest. One quiet tap, one sleepy soul at a time. But there is no need to do anything now. Nothing at all. You have traveled far tonight, through the channels and oscillations and quiet chemistry of a mind that has been tending to itself all along, in ways you never had to ask for. You can allow these thoughts of the sleeping mind to fade now, like the last slow wave crossing a cortex settling into stillness, leaving only the dark, warm calm behind. Let your breathing deepen. Let your body feel heavier, as if a gentle and patient weight has settled over you. The weight of having been understood, of having finally stopped, of being simply held. If sleep comes, let it carry you the way a slow oscillation carries a memory toward permanence. Not rushing, not falling, but arriving into a realm where time and weight no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they are closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, the glymphatic system will still be running. The hippocampus will still be composing. the body will still be finding its way toward repair. But tonight belongs to stillness. Rest well, sleepy soul. And remember, the most meaningful healing happens in the quiet you finally allow. Good night.